Okay. So last time, the last class we saw the units, fundamental units and derived units. Okay. So fundamental units are used for the fundamental quantities. Okay. So if you remember what are the fundamental quantities, there were 7 fundamental quantities, right? The length, mass, time, temperature, electric current, luminous intensity and the amount of substance. That's the last one is mole and all, which you use in chemistry. Okay, so among all these 7, let us see what are the basic. We will see look more into the basic units. See, that's one of the very important among these fundamental units. So from ancient time, the humans, only 3 units are very important. What were they? So they are length, correct. Length, mass and time. These are one of the 3 basic units which humans were using it for quite long. Okay, so other things were current and all, which came much later. So let us look more into these 3 units. Okay, so and what is the SI unit for length? SI unit for length is meter, symbol is m, mass is kilogram and time is second. Okay, so now, so let us look one by one of these fundamental quantities and how we are going to measure it. Okay, so measurement of first quantity, what is that? Measurement of length. Okay, so how we are going to measure the, first of all we have to know how do we define the length. So if you remember in the earlier class I said, so units means something, the physics what we use a quantitative science. So where you have to give number, okay, it's a number with reference. When I say something is how long it is, then I have to give some number, some with respect to some reference number, correct? And that reference is the unit. So in MKS units, the reference is what? Meter. So then I am going to define 1 meter. I am going to define a length, some length, and I call that as a 1 meter. And then I am going to define all other lengths based on this 1 meter. Okay, so first primary thing is I have to define the first unit. What do I mean by, what is the length which I am going to call it as 1 meter. Okay, so in earlier days people used this one. So in 1960, till 1960 and all, 1960 they started one way is what they did is this one. The standard for 1 meter is based on the wavelength of the orange red light emitted by the krypton atom. Krypton atoms, yeah. Oh, okay. What is that? So if you, in the later on classes you will see, the light is nothing but a wave. Okay, electromagnetic wave, which we'll see it in the later on classes. So what you will see is, so if I draw the wave, let us assume the wave is like this. So this is the distance x, okay. So, and I am going to call a wave something like this. Okay. So then this distance for one complete wave to fill. Okay, so this symbol is usually lambda. This is called as wavelength. Okay, either you can take it from word 0, or if you want, if you don't like that, you can take this one from the troughs. They both are basically same. Okay, so this is the lambda. So when I say orange red light of krypton, okay, every particular color of light will have a definite wavelength. Okay, so and these wavelengths are very different for different colors. So for example, if you remember sodium vapor lamp, the street lights, the yellow lamp, they have 2 yellow colors, which is a mixture of 2 yellow colors, so that each color has a definite wavelength. So similarly, mercury has a UV. Mercury emits in UV, that also has an fixed wavelength. Okay, for example, that's what your tube lights and all has a emits mercury vapor, which is as a UV. Okay, and that UV is not visible. So to convert them into visible only, you have that coating, the white color coating on the glass tube. So that in turn the UV light will be transformed into the visible light. Okay, so every color has a fixed wavelength, and every atom can emit light. Any atom. Okay, you can have the particular fixed lines they will emit when you emit. So what they say is, so they have to define, so when I have a different light emissions and everything, so then I have to define one particular light, and I have to define my wave meter with respect to that wavelength. So what I'm going to say is, what the people used in 1960 is, they use krypton atom. Krypton, okay? Krypton, right? Yeah, krypton atom, which emits orange-red light. So it's a fixed wavelength, one color, okay? So the wavelength of that light, it has a definite distance, okay? With respect to that, then they said, what should be my 1 meter? 1 meter will be equal to how many times of my lambda? So that's the way the people used in 1960s. Okay, so that definition was okay, but later on what happened after 1983, that has been changed. So why they changed it? Because by 1983 and all, there were many experiments were conducted, and you are able to precisely measure the velocity of light, at what speed the light travels. So then they use, because you know that velocity, speed formula is what? What is the formula for speed? Speed is equal to distance by time, right? So this will be typically, so you know, distance will be in meter per second, right? So now if I know some speed, and if I know what's the time, I can always define what is my meter is there. So what they calculated is the velocity of light, which is denoted by c. What they have, with all the experiments, how precisely they have calculated is, I'll write it down. So this is 2,997,9,2,4,5,8 meter per second. Okay, so the velocity of light is calculated in this precision. So then what will I do is, then I am going to write, let me write here time and then distance. And then I will know, so in 1 second, what is the distance traveled? This is the distance, right? 2,997,9,2,4,5,8 meter. Therefore, 1 meter is, the light travels 1 meter for how much duration? 1 divided by 2,997,9,2,4,5,8 second. So then 1 meter is defined as the distance traveled by the light in 1 upon 2,997,9,2,4,5,8 seconds. Okay, and remember, this is I forgot to tell you, this is the velocity, speed of light in vacuum. Okay, the speed of light differs in vacuum and different medium. In glass has a different velocity. In water it have a different velocity. You remember in your 10th standard you studied that, right? That's why the light bends. You have the refractive index and all. Okay, so what the measurement they say is on the vacuum. Okay, air and vacuum are more or less close by, so you can use it. But yes, for precise measurements they use vacuum. Okay, so since we know since the velocity of light is calculated at higher and higher precisions, then we can use that as a definition of a meter. That was more accurate than their red-orange light of krypton. So from 1983 onwards, they were using this as the definition of 1 meter. So then I have defined a scale. I have defined a reference value, correct? So at 1 meter is nothing but the distance traveled by a light in this many seconds. So then with respect to that, I can measure. So then if I say 10 meter, when I say 10 meter, so 10 meter is 10 times of the distance traveled by the light in 1 upon this much of seconds. You got it? So that become the reference, that become the, by that I am able to define the unit meter. So, so what happened? Why they keep changing is they want to make it more and more accurate. Okay, so this is when I know the speed more accurate than the red orange light of krypton. So then this is going to give you a precise definition of 1 meter. Okay, so that's the reason they keep changing it, updating it. Okay, so then what they have done is, okay, this is a unit of this fundamental quantity length we found. So then how do we measure the distance, measure the length? Okay, and that is very interesting. So for example, if I wanted to measure what is the length of this board, what is the breadth of this board, you can always take a scale and you can measure it up. Okay, so for smaller distance, typically you can always use this for the scale you have, and using that you can measure the length. But for larger distances, for example, I ask you what is the radius of Earth. You can't use a scale, okay? You can't use a scale and dig a hole through the equator and measure it out, okay? So there they would use different techniques. Or what is the distance of the planet, or what is the distance of a star. So these things are basically, we have to use a different ways to measure this lengths, okay? So, and okay, so, and interestingly, as I told this, the size of the Earth, actually first, what the way they found it is, it's during 250 BC. That means before your telescopes or anything is being invented. Okay, it is before Christ. Okay, so that means it is more than 2000 years before itself, people measured the size of the Earth without using any telescope or something. Okay, so how they were able to do it? Because they used to think. Okay, why they are able to think? Because they never had Android phone. Okay, so since they didn't have the Android phone, they were able to think. Okay, actually, I remember that. Okay, Eratosthenes. He is a mathematician. He is the one who derived the size, find the circumference of the Earth. He belonged to a period of 200 BC. 200 to 50 BC. That period itself, he measured the circumference of the Earth, not by running around the Earth. Okay, sitting on. The technique what he used is very interesting. So he is assumed. Okay, there is a reason why he has to assume the Earth as a sphere also. Remember those period, the flat. People were all thinking the flat Earth, right? At that time, this person has said, no, it is not flat. Okay, so what he had is he was from Alexandria. So he took two places. And he found, and for example here. So these are two wells separated by a certain distance, and the Earth is spinning. So this is the center, and let the Earth spin. Okay, and he was thinking sun is very far away. Okay, so sun is very far away, so sun rays can be assumed to be parallel towards the Earth, right? Because it's very far. So what happened? So when you are exactly at the noon, so the shadow, the well, this is the well, okay? This well will not create any shadow, correct? Because shadow will be on it. On the other hand, a well which is far away, this will create a shadow. Okay, so what happened? He noted, so he took two wells. Okay, then he noted the time at which no shadow is formed for this well. So, and he called that shadow, that time as T1. Okay, so then after some time, the Earth spins, right? Earth moves off. So then this came down to here, and this went to somewhere else here. Okay, so now this is not here, so this has moved here from now. Okay, so now, so earlier time was, so this one was measured the time as T1, correct, when it was there. Now, after some time, then this well had no shadow, so this time he called it as T2. Let us measure it as T2. Okay, so then he also knows the same well, now there is no shadow. It took 24 hours to get back to the same no shadow region. Got it? That means he understood the earth makes 121 to make one complete rotation, it took 24 hours. Correct? So then he simply used this form. So then he smartly what he did is, so he took, so this time difference, the time difference is what? T2 minus T1. Correct? This is the time taken. Correct? So suppose for, you can always find out. So this is at 5 o'clock, this is at 5 o'clock, and this is at 4 o'clock, then the difference is 1 hour. Something like that. So what he did is, okay, so what he took is, he wrote 24 hour, the earth made a rotation of 360 degree. Okay, so this is time and this is angle. Okay, and then, okay, oh sorry, yeah, fine. So then, so in 1 hour, it makes 360 degree by 24. Okay, so this is the angle. Suppose let us say this was the angle. Correct? So, and let the radius be, radius of earth be r, let this be theta, I'll use it in radian, and this length be drl, whatever it is. This is this length. Okay? So he knows, so in 1 hour, this earth is moved by this much degree. So he knows from T2 to T1. So therefore, T2 minus T1 hour, whatever the time, the earth would have made T2 minus T1 into 360 degree by 24. Am I right? So then he actually, so this is an angle corresponding to theta. Let us express it in radians. So this is the angle, he knows it. So then, we know, we have done in our, in mathematics, yes, right? What is that? Circular system and all. Okay, so if you remember, what is the circular system? What we had is, what did we write? Correct. Tell me, D is equal to R theta C, radian. Correct. From here, R equal to D divided by theta radian. Am I right? So, this distance he can measure, because what is the distance between the two wells? So he knows what is the distance between two wells. So he was able to measure T. So from the time difference, he was able to measure what is the angle. Okay, so all he has to put is that distance divided by the angle that give you the radius of the earth. Okay, so he didn't use any telescopes or any complex sonars and all. Okay, no ultrasonic waves or nothing. He just by sitting and looking at the sun, he was able to measure the size of the earth. Okay, and this is very interesting. So once if you know the size of the earth, okay, so once if you know the size of the earth, and then they were able to measure the size of the moon also, sitting on earth. What they did is, they took, they did it interestingly, what they first found is, what they identified as a ratio between the radius of the earth and the size of the radius of the moon. How they find is, so they take a snap of the moon during a lunar eclipse. Okay, during a lunar eclipse, what happened? The shadow of the earth will fall on the moon. Correct? So this will be the lunar eclipse. Now, so this radius will not be the real radius. Correct? Because this is the image you are seeing, smaller radius. But this will be the, if you actually draw, this will be kind of a similar triangles. You can draw and see. Okay, so then if I know the radius of this circle and the radius of this circle, okay, so then that ratio is going to be equal to the actual ratio of both the objects. Okay, so how did he find the radius of, how will he find the radius of this circle? That is the moon. That is simple. You draw two chords, take a perpendicular bisector, and take a perpendicular bisector. Okay, and where it cuts, this is the center. So this is the R moon. But this is the image of it, right? So I am going to call it as I. not real moon. Similarly, I want to find out the radius of the, again here I can draw two chords, take a perpendicular bisector, something like this here, and this gives your R, E, which is the image. So what, so therefore R, M, image, in the image side radius divided by R, earth, in the image radius will be, the ratio will be same as your actual size of the object. So this will be radius of moon divided by radius of earth. Okay, so you know radius of earth from here. Put it here, this ratio you can find it from here. So you can find out the radius of moon. So this is the way the large distance are calculated. Okay, and there, see those methods what I discussed, they were the very ancient way of measuring the distance, but people were able to measure even without any advanced equipment. They were able to measure the distance of the moon and earth and all. Okay, and later on what happened after telescopes, when you find telescopes and everything, what they were using the method is something called as a method of parallax. Okay, so the what do you call the parallax method? And parallax method is not very complicated, it's very simple. So what the idea, what the parallax method they use is, suppose I have a I'm looking at this finger, I kept a finger like this. So let me look at with one eye. Now finger is at the background, a different background. Now let me close this eye and open to this eye. The finger has moved from there to here. Correct? You see there's a motion of the finger. Okay. So now if I bring the finger close by and then when I open, it is going to move towards a larger distance, the background. Correct? So what I'm going to do, so I can see how the background shifts when I'm going to see from both the eyes. That is going to depend upon how far my finger is from my eye. Correct? So this was a simple technique. This was being used to find the distance. What is the way they do it out? So let us see how they find it. So let me have this as one of my eye and this is my another eye. The eyes are not of same size, let it be. Okay, so and what we are going to have is, let me say there is a point. So this is the finger I am saying, what I kept the finger. Okay, so then, so when I see through this eye, so this will be the direction. So this will be the background of something else. When I see through this eye, so this will be at a different background. Am I right? So these backgrounds are going to be different. Okay, there may be a tree or whatever, curtain or image, whatever it is. Okay. So now as I move the point close by, then this is going to become broader. That's not okay. So this background image is going to define how far the point is. When I'm going to bring the point here, this image is, the background image will be very small. You got it? So that will be very interesting. So, okay, so that we will see it on. So then, so now, so from this shift of this image, background image, I can actually measure what's the angle it has made. Correct? So this angle will be, typically this angle is theta, I can find. So this angle also will be theta because it's a vertically opposite angle. Okay, and then if I know this distance, okay, let me say this is quite far, that is this distance. Suppose this is what I'm going to call it as D, capital D. If this distance is very, very large compared to this L. So D is much, much larger than L. So then what happens? So I can always, instead of the straight line, I can assume it as a small circle. Am I right? It's a circle of a big radius. So this is a big radius. So then, if this is the circle, then this arc length also will be typically equal to L. Okay, so once I know L, once I know theta, then you know what the D is. Correct? What is the D? Tell me. So L is equal to, L is equal to D theta radian. Okay. So therefore, D is equal to L by theta radian. So by this you can actually find out all the distances. Okay, so any distant object you really don't have to go up to there. Just from the angle, take take two different points, and from the angle at which the background is shifting, from the shift of the background, okay, and then from the angle, and now I know how much distance my eye is, then this angle I know, and this eye distance I know, just I have to multiply this L divided by the angle, that gives me the actual distance of it. Okay, this is the way. Now, so the eyes are close by. So suppose now I am going to shift this point back much behind. So this point I am going to bring far away, maybe up to here. Okay, so then what happens? Then this line is going to be so this angle is going to become smaller, am I right? So if we keep it far away, this angle becomes smaller and smaller. At some point my background is not going to change at all because it is so far, correct? So then with my eyes, means either I see from this side or this side, that image far away object is not going to be different. They are the same background. In that case what happened? I am going to move from this place to another place. I will be here, I see what is the background, then I go some 1-2 kilometers ahead and I will see what is the distance there. So then, because when I separate this far away, then I can actually get a larger angle, then I can use it. Okay, this is the way your say distance of the planets, different planets. How do we find? Take two different locations on Earth. Okay, this planet is very far away. With my one eye, I don't going to make any angle. Okay, it's going to be very small angle. I can't do it with my eye. Just with my, sorry, not one eye, two eye. Just with my eye separation, I will not able to find the distance of the planet using this parallax method. So I need to have a larger distance. Instead of the eye, I have to move the eye over a larger distances. So what I am going to do? I take two different locations of the Earth. Okay, from there I take the angle. From that angle, I will be able to find out the distance of the planet using the same method. And well, that is for the planets I can do. Now for stars, the distance of a star, that is much bigger than the, much larger than the size of the Earth itself. When it is the distance of the star, the Earth will be like a point, right? The two different locations on Earth is not going to make a big angle. Very small angle is a bit tough. At that time what I do, I don't take the on the Earth, I take the position of the Earth during different times. Okay, because Earth is going to revolve around the Sun, which is going to be a larger orbit than the size of the Earth. Then I take a different positions of the Earth around the Sun's orbit. Then I use the parallax method and find out the angle of the, find out the distance of the star. Okay. So this is the way the parallax method is being used to find the large distances. Okay. So, and in the same way you can actually find out the size of the size of a planet also. Suppose planet is having a what is the diameter of a planet, or what is the radius of a planet? How do we find? So let me call this as a planet. Let this be the planet. Okay. This planet has a size, not a point object. That's why it doesn't twinkle. In Bombay, everything twinkles because of pollution. Okay, so then what happens? So I am on the surface. Suppose let us say this is the Earth. I am saying I am on the surface of the Earth. Okay, so then what am I going to do? So using a telescope, I can see the enlarged image of a planet, and then I can see what is the angle subtended by the two edges of the planet. Am I right? So now and I know this distance. That's parallax method, I can measure what is the distance. Correct? And what I want is this distance. Can you find? Again the same method. Correct? Again the same technique. What we will use? So d is equal to d theta. Okay, so by this you can actually find the size of the planet. So these all are basically parallax method. We can actually find it out. Okay, so Well, this is okay, fine. So now, this is by using this method, you can actually find the distance of planets, size of planets, or how far the star is, all within the galaxy. Okay, because my solar system is quite big size. Sorry, the orbit of sun is quite large. So, orbit of Earth around the sun is quite large. I can actually make a two different background angle. I can find out. Now, there are many galaxies. If I go out of the galaxy, so the galaxies are millions of light years away. Light year is another unit of distance. Okay, that is because when you have large distances, you can't use it by kilometer or meter or something. So what we use is a light year. Light year is what? One light year is the distance traveled by a light in 1 year. So you know that number earlier what we wrote, that in 1 second. So in 1 year means how much distance you calculate. Okay. And what I'm going to say is million light year. So million times of that distance, that is the distance of a different galaxy. Now solar system is our orbit of sun, that different location is very, very small compared to that. It will be like a point, much smaller than a point. Okay, then I can't use that distance to actually measure the distance of the galaxies. Okay, so then that is how do we measure those distances. It is not very easy. Okay, that's what comes under cosmology. Okay, so you need to know the Big Bang theory, the Hubble expansion, from the Hubble expansion velocity, how do we measure the distance of those galaxies. And okay, so then it's you can read any popular science book and you will understand how they are doing it out. Okay, okay, that's what they call a redshift. Okay, fine. So with that, this is the way they measure the distance or being measured. Distance of means a large distance are measured. Yeah, and there's one more thing is okay. So this is for the larger distances. So now take a smaller distance. Okay, I am asking what is the thickness of the paper. Now you don't have a scale. You can't put a scale and find out the thickness of the paper. There is something like it's very small, right? So then what happened there? You use something called a vernier caliper, screw gauge, and the small vernier calipers. There are different instruments are there to measure a smaller distance. In a laboratory, you will use those vernier calipers and screw gauge. That's to measure thin, like suppose the thickness of a paper or a cardboard. Those things you can actually find out. Okay, or a small tube. What is the diameter of a small tube? So those things only you can find out. But now if I'm asking much thinner objects, much thinner than this one, say a foil or a film. Film is what? So for example, I'm going to heat up a metal, melt the metal and evaporate it. So the vapors will come. I'm going to deposit that vapor on a glass slab. And then I take the glass slab and that glass form a very thin layer of the metal film is there. Now you can't use a screw gauge and tighten it and all those things. Okay, how do you going to measure that? Those things you will use it when you make a small object. You use it a microscope. Now if you want to still further smaller one, there's an atomic structure level. Then you use a telescope called as microscope called as a electron microscope. Okay, the smaller distances you started using the microscope to measure the distance. The larger distance you will use telescopes to do it. Okay, measure the distance. So this is the way the length is measured. Okay, and that's all. Okay, and there are something in the astronomical unit they have done. This you can read it. Okay, they are not very tough. Okay, and there's a Fermi meter, 1 Fermi. That's a very small meter. Angstrom. These are all very small length. You can read those things. These are not very tough. Just as a story there. Fine. So then we are going to the measurement of mass. Okay. Yeah. So we found the second quantity, fundamental quantity is a mass. Let us try to see measurement of mass. Okay, so again here I have to define. So in my SI units, the mass is defined as kilogram, right? Then I have to say what is the mass you call it as 1 kilogram. So with respect to that, I can say other thing. First I have to define what is the mass, which I call it as a 1 kilogram. So that's what the people they used is, I think it is still since 1889. Since 1889, what they were using? They were using a alloy of platinum and iridium. So what happened? There's an alloy, metal alloy, a piece of metal is a shiny metal of platinum and iridium, which they named as this is 1 kg. Okay, so all other measurements are based on that 1 kg. So that metal is being protected very well in a glass box or something, so that weight should not change. But even if gold is measured with that compared to that. Okay, so it should be very precise. So that weight has to be very constant, that has to maintain. But over the time, what the people found is the weight is actually changing because due to the dirt in the atmosphere, even though however you are protecting, the dirt is getting accumulated and the atmospheric effects and all, the weight is slightly changing. So it was not being that precise. Okay, because that's what I am going to use it for my unit of weight. Now, if it is not precise, all my calculations will have the same. You will see in the later on this chapter the errors. So this error that will keep adding up in all my work later on, which I am using this one. Okay, so because then I am not, when this, see today I keep a metal and I call you this is 1 kilogram. Let us use this as a reference and see I can't use me as a reference. I'll say okay, I am the 1 kilogram or say some unit. So you use me, every weight should be made with respect to me. Then it's not going to be correct because tomorrow I am going to get old. My weight is going to change. Then at the time I am the 1 kilogram. Okay, so I can't do that. So you need to have a weight which is very precise, which doesn't change with time or something. Okay, so what they found is this is changing with time. Okay, so then what if they had to invent for it happened last year, May 2019, they used a different way to measure to define the unit of mass, kilogram. What they call it as a Kibble balance they used. What is that? Kibble balance. That's very interesting balance. Okay, so I am not going to exact how this balance looks like. We can very simply we can understand what the Kibble balance is. Suppose we have a balance. What's a balance? You know the physical balance, right? So there are two pans. And there will be a needle or whatever the indicator, okay, which says whether the balance is proper, when it is normal or not. Okay, so now what I am going to do, I'll put a 1 kg here. So what is going to do? This is going to pull this pan down, correct? So then now my pan has moved here. And so the balance also moved like this, correct? So now the pan is something like this. Now what am I going to do? I will keep a magnet here. Not the normal magnet. I am going to keep an electromagnet and pass a current. Suppose, and if I keep increasing the current, this is going to attract this pan. Okay, so this pan will start moving down because of the attraction. So I will find out what is the amount of current it is required so that the pan comes back to the same volt value. As I keep increasing the current, the pan will keep moving down. At some value of current, it is going to maintain it. So then I define this current, the current at which my 1 kilogram is coming and setting up. I will define this current I use this current as a measure for this 1 kg. So what happened? So if I wanted to take any material of 1 kg, I just give the same amount of current and put the material, keep adding the material till the balance comes to normal. Okay, so this is a Kibble balance. So this is now used for a very precise measurement of masses. Okay, nowadays they have all this vacuum and all. So no dirt, nothing will stick up. The very, very sensitive instruments they make. Okay, I drawn it a very simple way, but actual experiment will be very precise. Okay. Okay, so this is for the heavier masses they will do in. Now, and yeah, okay, similarly for heavy mass, like same thing in a distance, you have the heavy mass also. Suppose like mass of Earth, mass of a star or something, okay. There we use different techniques, which is not in your book, which you will see in advanced class. Okay, maybe in the laws of motions. When you have laws of motions, there you can actually, from the movement of the objects, you can find out the mass, or if a star, how much brightness the star is, the light emitting, how much radiation emitted. From there also you can actually find out the mass of the star. Those are different techniques. Okay, so they are. We will not see those things now. And similarly, okay, for very small mass, that means very, very tiny mass. Okay, then I can't use this kilogram unit. Am I right? Then what happened? There I use a we are going to atomic scale. Then I will use something which is called as your atomic mass unit. You heard about it, right? In chemistry, correct? Okay, what is atomic mass unit is? So what they say is an abundant isotope on Earth, that is your C12, carbon 12. Okay, is a carbon 12 isotope. It has 6 protons and 6 neutrons. What they say is 1/12, 1/12 of the C12 mass. This is called as a 1 atomic mass unit. Okay, 1 atomic mass unit. So in kg, this will be typically equal to, you know the value? Tell me. 1.6 something, right? 6605, 6605, whatever it is. Okay, in 10 to the power of minus 27 kg. Sorry, 27, right? 27, I wrote 20. 27 kg. Okay, so this defines. So yeah, okay, by this I am going to make a smaller unit of the quantity, fundamental quantity, mass. This is used for the atomic calculations and okay. So this is how the second fundamental quantity, mass, is being measured. Now let us go for the third fundamental quantity. What is that? There's a time. So time is also, we need a precise measurement, right? Because these three are very important quantities. So that is your time. So again, so for quite long, people were using this, using something called as your mean solar day. What they say, what is a mean solar day is, so suppose you have a, your shadow, today you are falling, the shadow is exactly falling on your foot. If I don't change, when next the shadow will fall on my foot? After 24 hours, correct? The earth makes rotation. So it's something, any pole or something, when its shadow exactly fall on its foot, okay? So, and it after 24 hours, it won't be exactly 24 hours, there will be slightly change in every day, day to day, okay? So what they say is they take a mean of it. So that 24 hours is called as a solar day. So you take a mean solar day, the time, okay? And that mean solar duration, that duration is your 24 hours. Okay, and that will be equal to 24 into 60 minute. And that is equal to 24 into 60 into 60 second. That's equal to how much? 86400 second. Shakuntala Devi. Okay, so 24 hours is 864,000 second. I remember because we use it often in our work. Okay, we use in seconds. Fine, and 24 hours second. So from here I can easily define second. Therefore, 1 second is equal to, tell me, 24 hours is a one solar day, correct? One mean solar day. Oops. One mean solar day. Am I right? That's equal to 24 hours. So 1 second equal to 1 by 86400 of mean solar day. So this was the definition of, this was used as a measure of time, the unit. Okay, again time also is reference value, right? This was. So 1 by 86400 times the mean solar day, that was used as a unit of time. That's a reference. Then all other times are measured in terms of that unit. Okay, but as I told you, that is not going to be always same, because what they found is the the spin of the earth slows down. Gradually it's slowing down. So then since it's slowing down, it's going to take more than 24 hours. Correct? Then my definition of second is not going to be same. Okay, see, for what happened, all the units has to be remain same whatever the time, wherever, whenever it is you are using. The moment if it is changing, then my whole calculation is going to change. Correct? So because then my unit second is no more a constant, same, it is going to vary depending upon it. So then what I found is this is not a very precise measurement of second. So what they use is something called as atomic clocks. Okay, so that you will read it later on also. What they say is a cesium clock. See, even periodic vibrations produced in a cesium atom. See, all your there are certain atoms which also have they vibrate, okay, and they have a characteristic frequency. That frequency is more or less precise. For example, quartz. Quartz also has a more or less stable, steady vibration. Okay, that's why all these clocks what we use, they are all based on the quartz crystal. This is called the quartz clock, because there's a quartz crystal, and that quartz crystal vibrations are more or less precise. So they use that vibration. Okay, that vibrations is converted into 1 second by using the gears and all, and then from 1 second to minutes and then hours and all using gears, and that's how we make it all these wall clocks and all. Okay, but quartz, even this quartz vibration is not very precise. Means you see that all clock manual they will be written what is the precision. So after how many, it's very precise, more than many years it will shift by 1 second or something. Okay, so that precise. But even that is not allowed when you want to have an accurate time measurement. So then I need to look for more and more precise ways of measuring the time. So I won't use a quartz. Rather what they use is something called a cesium. Okay, the cesium vibrations are more precise. They won't change at all. So then I can use that as a standard to measure my 1 second. So what it says is, okay, it's written is, so you can actually find it out. So the 1 second, so what happened? The time taken for the cesium atom, the vibration of cesium atom, time taken for, this is huge number, 9,192,631,770 vibrations. Time taken for by a cesium atom. Cesium spelling is C-E-S-I-U-M, cesium atom. Time taken for this many vibrations by cesium atom is 1 second. Okay, and this is very precise. This is because this is not going to change. So this many vibrations is not going to change at all. Even today or tomorrow or maybe 10 years or 20 years later, this vibration is still going to make the same duration. So then I can use that as a precise measurement of time. Okay, so that was being used as your measurement of time. And that's it. Yeah, fine. So this is the way so in earlier class we saw the fundamental units and the derived units, and one of the very important fundamental units are these three: length, mass and time. but this is being used extensively in our life. Okay, for every measurement, your satellite sending a satellite signal, everything, all your GPS and everything, they use this very precise length, mass, time measurement. If you don't do it out, so then there can be a havoc. For example, even when you are landing a flight or something, even a very small mismatch, okay, it can cause your flight to crash. Whatever altitude, what they say. See that when the flight is landing down, it needs to know what's the altitude from the ground. Accordingly, it can land it. Okay, so these are many things. So this is for all these measurements, you need this precise of these three fundamental quantities need to be as precise as possible for our technological life today. Okay, so then that's what these units are being. Earlier we had a different form of units. We are being more and more precise. Okay, so for length we started using the velocity of light, because we know the velocity of light is one of the very precise quantity. So once I know the velocity of speed of light very precisely, then I can define what do you mean by 1 second. Then for the length, what we use, that this one. Length only I said velocity of light. The next one is what? Mass. Mass we can use a Kibble balance. Okay, well, the correct. And for time we use a cesium clock. Okay, so this is the till now this is the most precise things we have. But tomorrow, in the later on, when we need more and more precision, we will get more precise measurement of. See, even this, nothing is precise. There will be always a small deviation. Okay, that happens in over million years or maybe 100 years or something. But if I want to know even a precise more than that, then I need to go for a better definition of these units, and then I have to get something more precise one. So that's why it keeps changing. Okay, so 100 years later from now, someone will see this, what the sort of units we are using. Okay, they will have more precise measurements of the units. Okay. Okay, so in the next class, we will see about something, what is the dimensions and the dimension analysis, and that's very interesting thing. Okay, because this dimension analysis is one of a very important technique when you are trying to figure out many problems. Even up to your PhD, you will use it. Even if you are doing a PhD, you will use dimension analysis. Okay, that we will see it in the next class. Okay.